So this video for the distribution shapes will be quick. As you can see, this is a short set of notes, and this is going to tie into everything we looked at with stem plots, when we've looked at histograms, and we're going to build upon these distribution shapes because we're going to have to start talking eventually about normal distributions and how this data that we are kind of analyzing right now is going to come together into something that is understandable mathematically and allows us to make predictions based upon the data that we're given. So the definition of the distribution of a data set, you can see right here, is the distribution of a data set is a table, a graph, or a formula that provides the values of observations and how often they occur. So how often they occur would be a frequency or a relative frequency. And that's how we've portrayed things up to this point. We've looked at frequency distributions, we've looked at relative frequency distributions, frequency histograms, relative frequency histograms, dot plots, stem and leaf plots, pie charts, bar charts. So right now we're okay with all those. Just a quick side note, shortly after I finish this video, I'm going to have dinner, and then I'm going to make some quick videos on how to do histograms, bar charts, dot plots, and pie charts on Google Data, or not Google Data Studio. You guys would hate me if I started using that. On Google Sheets. So there'll be individual videos so that you only can have to reference whichever video you need to create whatever kind of chart you're working with. One other thing too, I don't know if everybody saw the message, but I did create a shared Google Drive for all of us. The email for that drive is ekustats270@gmail.com. The password is Jaronscat, JARONSCAT, with all lowercase, one R only. When I sent that out to you all, I already had a couple of you get back to me and say you couldn't get logged in. That's because I sent you the wrong password. Anyway, as far as that Google shared Google Drive goes, I'm going to put folders in there for your assignments, and you can upload them directly to that instead of emailing them to me. That way I don't lose anything through email. And then it also provides you all an opportunity to continue to edit it if you need to up until it's time that I grade it. So we are talking about distributions. So here's just a sample distribution. We have a relative frequency histogram that shows the heights of 3,264 students who attend a Midwestern college. You can see by this information, just looking at the histogram itself, we've overlaid it with a smooth curve, and that smooth curve is what we're focused on. This provides us with some general ideas about the heights, how they're distributed, and then we're going to start looking at the mathematical implications of this later on and how we can compute these curves. But you can clearly see how that curve kind of does fit the histogram that's provided. There are several different types of curves that we will encounter. The predominant one that we're going to see the most often is a bell-shaped curve, and those bell-shaped curves can be right skewed or left skewed. That's going to be the traditional curves that we're gonna look at. We'll seldom see triangular. It's very rare to see a uniform or rectangular distribution. The reverse J shape and the J shape curves come up sometimes. Typically that's when you're looking at exponential growth, exponential decay. And then these other two down here in the bottom right, unimodal, or sorry, unimodal is not on there. Unimodal would refer to a bell-shaped curve that you see at the top right or top left. The bottom right, we have bimodal and multimodal. Bimodal means that the histogram or the curves have two distinct peaks. Multimodal means that maybe it has several peaks, any number greater than two. Typically, a lot of the information we're going to see should fall into the single bell-shaped unimodal category. Very occasionally we might run into a bimodal distribution. Seldom will you see a multimodal distribution. So just to kind of put this into practice with how does all this work together, here's a relative frequency histogram that shows the distribution sizes of households in the United States. And we want to determine, is this roughly symmetric? Is it right skewed? Is it left skewed? Um, Based upon just the histogram itself. So let me choose a color that will show up. I'm going to go with red. So if I kind of match a curve to this graph, starting here at the origin, we have a unimodal peak, and then everything starts to kind of taper off as the number of people in a household gets larger. So if we were to classify this, it does not appear to be roughly symmetric, because symmetry would imply that, and even rough symmetry, that it's kind of if you split it in half, it may be a mirror image of itself. This one clearly is not. If I split this in half, say right here along this blue line, that almost exactly divides the data set into two equal halves. That is not a mirror image, not even roughly a mirror image. So we can simply say that this is definitely not roughly symmetric. So it has to be right skewed or left skewed. When I took statistics, right skewed and left skewed always threw me off. But it's really pretty simple once you kind of sit and think about it. Right skewed means that this graph has what we would call a right tail. It gets closer and closer to the horizontal axis. Left skewed, the tail is on the left hand side of the bulk of the data, so it kind of approaches the horizontal axis going towards the origin. So this graph, if we look at it, it is going to be definitely right skewed, because the data is getting smaller and smaller. The values are getting smaller and smaller and smaller the further out we go to the right hand side of that line of symmetry that I sketched in there. So this graph is certainly right skewed. Because the data values get smaller and smaller as we move out towards the further right extreme values on the axis. The bulk of the data clearly lies towards the beginning of the initial values 1 and 2. Then it immediately drops down when we get to 3, 4, 5, 6, 7, and so on. Stuff isn't really that hard. Modality, again, this is where we talk about the number of peaks. I kind of addressed that when we looked at the different types of curves we may encounter. So simply looking at the number of peaks, that will help you understand what kind of graph you're looking at. So we have unimodal, bimodal, multimodal. Those are only 3 types. Unimodal would be the example we just looked at. It has one distinct peak. You really couldn't possibly interpret that any other way as having more than one peak. So it is a unimodal distribution. Bimodal, 2 peaks. Multimodal, more than 2. Symmetry and skewness. We just kind of addressed that too in the first example. This set of notes is not example heavy because it should be pretty straightforward. Symmetry we did talk about. If you kind of split that whole graph in half, you split that x-axis in half with equal data values on the left, equal data values on the right, numeric data values. Then if you kind of imagine that as being that line that you draw as being a mirror, do they roughly reflect one another? And when I say roughly, I really do mean roughly. If they kind of look similar, then you can say, yeah, it's roughly symmetric. Otherwise, you're going to have a situation where it's going to be skewed right or skewed left, like we saw in example 1, which was a right skewed graph. Population and sample distributions. We've discussed these terms extensively already. We know the population is what we want to study. The sample is a representative portion of the population that provides us with information. And just a little note here, sometimes any kind of study that studies the entire population exclusively, not taking samples, but actually questioning the entire population, surveying the entire population, is called a census, no matter what the population is. It does not have to be people. It could be whatever you might be studying. Maybe fish, bears, who knows. So the distributions of the population and the distributions of samples within the population should roughly mimic one another. We're going to see that here in example 2. We're going to refer back to the graph from example 1, where we have the relative frequency distribution of the number of people in the households for the entire United States. That's what this graph here in blue represents. It is not a sample set of data, it is a population or a census. So this does show in this graph that I've just now boxed in with this beautiful pink square, that this is exactly what the population looks like. This is how it is distributed as far as the number of people per household is. So then if we took simulations, and so that's what I did to get these other 6 graphs over here on the right. We took simulations of 100 random households, and I've done that per graph. So there's actually 6 different 100 sample distributions represented here. You can see every single one of these graphs, there are minute changes as compared to the census data, but they are all roughly similar to the census data that we're given. The one that stands out the most to me as being having the largest difference would probably be this first one in the second row, because we have a steeper drop between these two sets of 2 data points. But I mean, nothing really jumps out though as being obviously a glaring error might stand out somewhere. So these samples do seem to be very representative of the population. So this just kind of gives you another point of illustration to show you that if your study is conducted correctly, your sample will end up being very, very similar to what we would expect of the population. And that's what makes one of the nice things about statistics, is what makes it pretty easy to make a lot of predictions and to extrapolate information based on what you're given. And that's what kind of something I just touched on is mentioned right here where it says key fact. For a simple random sample, the sample distribution approximate the population distribution. The larger the sample size, the better the approximation tends to be, and that makes perfect sense. We wouldn't want to just sample 10 people in the United States to try to be representative of the entire United States. That's not going to be very helpful. If we limit our population to the school, roughly 900 students, a sample size of 50 to 100, 100 is more than sufficient. 50 is probably perfect. And it's going to be a judgment call based on the person conducting the study. But this just gives you a quick idea of what these distribution shapes look like. I think that is the end of that. Yeah, there were the homework problems. So shapes pretty easy. The homework not going to be too difficult. We'll address questions for sure if you guys have them. I think we're probably going to spend a little bit more time tomorrow looking at 1.6 and addressing questions on that, playing with Google Sheets a little bit more, just to get you guys comfortable with this. So if you guys have questions, you know how to reach me. I hope everybody is having a wonderful evening. I was glad to see you guys for a little bit this morning. I just really do appreciate you all being patient with me while I try to start juggling my own personal school schedule. Those Mondays are going to kill me sometimes. I managed to make it all day today and forgot to eat. You guys are going to have to remind me to eat from time to time. So just check on me periodically. Say, hey, have you eaten yet? Because I actually forgot. But anyway, have a great night. I will have a few more videos out later for Google Sheets, but that's it. So I'll talk to you guys in the morning.